In this lecture, we are going to answer the PCH 321 past questions, and this will be question 4 of one of the past questions that was given. Now, we have a synthetic route for the synthesis of this compound here. However, this synthetic route, it has several other reactions that actually took place for us to get to the last product here, which is this. Now, you are not concerned much about the naming or any other thing. The questions that they want you to actually prefer, or the answers they want you to give to the individual questions in these reactions, we are asked in the next slide. So what we are going to do is just to take a look at the reaction, the synthetic pathway, and then look at the individual reaction. What reactions do you think they are? Is that okay? Now, I'm going to take, for each question you see here, I'm going to take a portion of it and then explain that particular question. So we have the first question. Say, what is the name of the reaction A and illustrates the reaction mechanism? Now, this is reaction A, which is the first reaction that involves this is a diene, a cyclodiene, and acrolein, which is called a dienophile. And you know that a reaction between a diene and a dienophile is called what? It's called the diadase reaction. It's a cycloaddition reaction, 2 by 2 cycloaddition reaction. All right, 2 by 2 cycloaddition reaction to form the desired products. This here is the diene and this is the dienophile. So if you are to write the mechanism of reaction, the first thing you need to do, or the first thing I would advise you to do, is draw the structure in such a way that you have it like this. Look at it. This, the diene with double bond here, and then you have the dienophile. In this case, the dienophile is acrolein, which is this structure here. And then, of course, let me bring this one down a little. You have this here is CH2 or H2C, and then of course you have the double bond here, and this group I can decide to write it like this, and there's this CHO. The reason why we have to put it like that is so that it can easily react with it. This and this are the same thing. Now, how does this reaction take place? Firstly, says that this dienophile is diene loving, hence it can actually attack the diene double bond. So what will happen is that this double bond here will come here, there will be a linkage here, and this one will pack here. If this double bond is packing here, what will happen? This other double bond here come and form another linkage here, and then the product of this reaction will be something like this, which is this product you can see here, because the double bond will come here. Are you getting it? Then you have this part like this, which is like this, and then you have this linkage. Let me just draw it. You have a linkage here and another linkage here. This double bond will no longer be there again because it has moved to this place. This double bond will still remain, which is this other one here, and then this one is the one that formed this linkage here. So the product of the reaction will be this, which is something like this. All right, we have a double bond here, and then you have something like this. All right, this is the product of the reaction, and this is what you are actually expected to do, because we are told to illustrate the mechanism of reaction, or the reaction mechanism. So this you have here is what we call the mechanism of the reaction, or the reaction mechanism. Here, make this here is called the mechanism of reaction. It's a 2 by 2 cycloaddition reaction. Is that okay? So that is one thing that you should take cognizance of, and it's just by, I think, the reaction condition they just hit. All right, so that is that. Now let's look at the next question. Now everything you are seeing here actually came from here. That was why I said I will take individual portion of this synthetic route that actually concerns the question that was asked. So for this first one, and what is the name of reaction A and illustrate the reaction mechanism? So we took the parts that contain reaction A and we've illustrated. Now the next one is, what is the function of the reagent D? Now reagent D, you can come here and say reagent D is what? is H2 and palladium. H2 and palladium, they are reducing agents. All right, so that is the function of reagent D. They are what? Reducing agent. Now, what did they reduce? They reduce the double bond of this cyclic ring here to saturated compound. So there's no double bond here. Is that okay? So that's basically the function of reagent D. And this is what they are asking you. This D here, what is the function? It's a reducing agent. And that is that answer to that particular question. All right, let's see the next one. The next one says, what is the product of compound C when treated with sodium borohydride? Now, when treated with sodium borohydride, compound C will selectively reduce the aldehyde functional group. This group here is what we call the aldehyde group. All right? The aldehyde group. And aldehyde group are easily reduced by what? By sodium borohydride. Something like this. You have aldehyde arrow, C double bond O. If you look at your material, when you pass them through sodium borohydride, it's going to reduce them to give us alcohol, which is something like this, OH. This is an aldehyde, all right? And this is an alcohol. And in this question, this particular one here is the reagent that we ask. All right. So whenever you treat this one now with sodium borohydride, this entire molecule with sodium borohydride, this is what is going to give to us. You are going to write it out first. You have something like this. You have something like this. Sorry about this. Then you have the double bond here, and then you have CHO. It's going to selectively reduce this one here to alcohol. So the product of this reaction will be something like this. And then here we give us CH2OH. This is the alcohol group that has been reduced. All right. So you should take note of that. Now, sodium borohydride reduces alcohol. Now, you can see that under the reduction reaction, you know, this particular material was on oxidation reduction reaction. All right, so that is that question. Let's look at the next question. The next question says, what is the function of O3 at H? Function of O3 at H. Now, if you look at this reaction very well, O3 is what? Ozone. Now, and you agree with me that ozone in this reaction is what actually aids in the process we call what? Ozonolysis. Ozonolysis. Are you getting it now? So if you are asked, what is the function of O at H? This O3 rather, which is ozone, it helps in, can we say ozone helps in oxidative cleavage? Oxidative cleavage to ketone. It helps in oxidative cleavage to ketone. In brackets, you can put ozonolysis. Are you getting it now? That is the work of ozone. Now, if you look at it, if you studied those videos already sent earlier, you agree with me that I said in ozonolysis, what actually happens is that at the site of the double bond, it will actually break. Now, when it breaks, this part of the double bond, oxygen will attach, and this other part, oxygen will also attack. Is that okay? But in this case, the only product you have here is that of the oxygen here. So O3 is an ozone, and it helps in ozonolysis, which is oxidative cleavage to ketone, in bracket, ozonolysis. So that is the correct answer to that one. You don't need to write much. And then the next one, what is the role of sodamide? This compound here is a very strong base. And the name of this strong base is called sodamide. Now, and then we have methyl iodide. Methyl iodide, still the same thing as CH3I. Now, what is the role of sodamide and methyl iodide in this reaction? Now, sodamide is acting as a base. Let's take it that way. A strong base. In fact, you must state it. That sodamide is acting as a strong base. Are you getting it now? Which will abstract acidic protons. Now, if you look at this reaction very well, or this compound very well, what you have here is ketone group, which is ketone C double bond O. Now, listen to me. Okay, it was this reaction that came to this place. It was this reaction that came here. Let me put it like this. This reaction came to this one. So we have the keto group here, which is the ketone group. Now, if you have knowledge of chemistry, you agree with me that this position here, what do you think we have at those positions there? We have hydrogen, hydrogen. These hydrogens here, in chemistry, we call them acidic hydrogen. Acidic hydrogen. Why? Because of the presence of this double bond here. Is that okay? And this hydrogen also is what we call what? The alpha hydrogen. If you can remember, alpha hydrogen. And we learned something about enolate ion and aldol condensation reaction. This is also a reaction due to the alpha hydrogen of ketone and aldehyde. Now, if you come here also, there's another alpha hydrogen here, because if you count this 1, 2, 3 plus this one, making it 4 bonds, right? So there is an alpha hydrogen here. There are 2 alpha hydrogens here. These 2 alpha hydrogen are acidic hydrogen because of the presence of this ketone here, which inductively withdraw electrons from there. But that is not even your major business. Your major business is to know that these 2 here, they are alpha hydrogen. And what did we learn about aldol condensation reaction? That a base, a strong base, can actually withdraw electron, right? They can withdraw, they can abstract a proton, if you learned aldol condensation, from an alpha hydrogen. Can you still remember that when we said something like this, that if we have arrow, C double bond O, and then you have CH2, we said CH3. We said that for aldol condensation reaction, this CH3, we can also write it as what? CH2 and then H, where we said that we can use OH, which is a very good acid, to abstract this proton from here. And when we abstract this proton from here, what will happen? This one will form a negative charge here, which is a perfect nucleophile that can attack another aldehyde to give the desired product, which is a beta hydroxy ketone or a beta hydroxy aldehyde, depending on the nature of the reacting species, whether it's an aldehyde or a ketone. Please refer back to your aldol condensation reaction. Now, same process is what is going to take place here. What is going to happen is that this sodamine, the amine group of sodamine, which of course is a very good base, NH2, we abstract a proton from here. And if it abstracts a proton from here, we are not told to write the reaction mechanism. But I want to show you why I will call the reaction the name I will call it at the end of the day. Okay, so we have something like this. We have double bond O, and then we have hydrogen. These hydrogen are there, but you can't see them. Now, this sodamide, you can split until you have the what? The sodium, the amines ion, which is NH2. It has a negative charge. This is a good proton abstractor. This can abstract this proton from here. If it abstract this proton from here, what will happen? This bond here will kick in here. If it kicks in here, what will happen? This one here will kick up here, right? Now, just follow what I'm doing. Nobody asked you for this one, but I just want to show to you why we call it the name I will call it at the end of the day. And then this one, give us O. Of course, we have negative, and then here will now become a double bond. True or false? Then we have one hydrogen here. Then this other hydrogen add to this to form ammonia, right? But that one is not your business. So we have a double bond here. Now, this double bond here can also act as a nucleophile. Do you remember SN1 reaction? Here we say if we have something like this, CH3I, this now cannot act as a nucleophile, right? You know why? Because if this double bond here is a nucleophile, you already know that double bond is a nucleophile, right? So this double bond will actually attack this CH3 so that it will form a linkage here, which is CH3 here. And then we said that this I will be a good living group that will actually leave this place. Is that okay? So that at the end of the day, let me put it this way, the product that will be formed will be in such a way, if this one came here, this living group leaves, and then this one will come back again to form its double bond. So what you are going to form at the end of the day will be something like this. Of course, double bond will be formed back, and then of course you have your CH3 that is now added, and then you have hydrogen. Why? Because this one here will leave. This entire process here is an SN2 reaction. Why? Because we use a primary alkyl halide. This is like the nucleophile. You know what SN2 reactions say? Says a nucleophile reacts with what? An alkyl halide. What do you have here? This is an alkyl halide. Are you getting it now? This here is an alkyl halide. So a nucleophile reacts with an alkyl halide to form the desired product. Now this other one here too can also undergo the reaction again until two methyl group are perfectly substituted for this position. All right. So without saying much, if you are asked what kind of reaction is this and what is the uses of each of these, I've told you that sodamine in this reaction is acting as a what? A base. In fact, a strong base to abstract, right? You can write it, to abstract alpha hydrogen. You can write that. And then the next thing is methyl iodide. Methyl iodide is still the same thing as CH3I. This is an alkyl halide, and it is acting as a what? A substrate. A substrate, right, for SN2 reaction. Now, because we are not giving this directly in our notes, you can say it's a substrate for SN2 reaction 1. You can also say that it provides the alkyl group. It provides the methyl group on the ring. All right. So that is that. Now they say give the name of the reaction. Now I can have different names to give this reaction. There's no specific name for it. But if I want to give the name of the reaction, I would say this is alkylation of enolate ion. Alkylation of enolate ion via SN2 reaction. Alkylation of enolate ion via what? SN2 reaction. Is that okay? So that is that. Now let's see the next one. Convert compound K to I using an alternative pathway. Now I want to convert compound K to I. Where is compound K? To O rather, using an alternative pathway. It's coming from this way, right? Compound K is a ketone. Forget about this group here. Maybe they forgot to add it here, but there was nothing that was actually done here to remove this, right? So if you want to convert this to this using an alternative pathway, one way to do that is to use the Wittig reaction, right? You've already learned about the Wittig reaction by now. So the only thing I will just do for you is to just show you the reactant that will actually react. You don't need to write the mechanism. The reactant that will react for Wittig reagent, we say we use pH 3, then CH2 plus what? Heat at a particular temperature for hours. All right, there is a particular hour that they actually give heat for 12 hours. For like 12 hours, it mustn't be really 12 hours, some 10 hours, but I'm going to use the 12 hours. 12 hours, and then of course you have 18. In 18, this is going to give us the desired product, which is this. So this is an alternative pathway for synthesizing compound O, not following this normal pathway. All right, these groups here are supposed to be there because nothing actually remove them, but since they didn't show, the most important thing that they are actually interested in, or the examiner is interested in, is how you can actually get from here, which is this aldehyde group, to CH2, is by Wittig reaction. So you can come here and write Wittig reaction. All right, so that is that for that question. Let's see the next question. The next question says, outline the synthetic utility of L. Now, L is Grignard reagent. L is a Grignard reagent, which is methyl magnesium iodide. If you want to write it out, you say CH3 magnesium iodide. Now, outline. When they say outline, just state the synthetic utility of the Grignard reagent. One, Grignard reagents, they react with alkyl halide to form higher alkane. Sorry about that. To form higher alkanes. All right, those are the synthetic utility for the Grignard reagent. For instance, you can say this H3C, and then you have MgI plus CH3 CH2 B arrow come in here. Now, at the end of the day, what will happen in this reaction is this group here will bond with this group, and then these two will combine together to form H3C CH2 CH3, which is propane. So this is a higher alkane formed, and the name of this higher alkane is propane. Are you getting it now? So that is one of the synthetic utility of Grignard reagent. Now, Grignard reagents, they also react with terminal alkyne to form alkynyl magnesium iodide, which when treated with alkyl halide yields higher alkyne. Are you getting it now? Grignard reagents, they react with terminal alkyne. Now, the reaction is more like the reaction that we looked at not quite long. Let me just erase from here so that we can see some space to write. They react with terminal alkyne to form the alkyne magnesium halide. All right, or alkynyl magnesium halide, which when reacted with alkyl halide gives alkynes, higher alkynes. Now, how is this even possible? You have something like this. Let's say H3C C triple bond C. This is a terminal alkyne. Why? Because it has this double bond here, triple bond at the last carbon. If you react this with a Grignard reagent, now the first thing is going to do, in this case, let's use this one. The first thing that is going to happen is very easy. This group here, hydrogen, will bond with CH3, and then this magnesium iodide will come here. So what are you going to have? You are going to have something like this. H3C C, triple bond C, and here will become magnesium iodide. Now this magnesium iodide, which is this group that is formed here, if you react it with CH3I, this is going to form, let's say, methyl iodide. It's going to form the product whereby these two things, this one here and this one will combine. So we are left with CH3. So you're going to form something like this. Let me just write it this way. CH3C, triple bond C, CH3. So it's no longer going to form a terminal alkyne, but other alkynes. So that is another synthetic utility of Grignard reagent. Now, what other synthetic utility of Grignard reagent do we know? Grignard reagent react with aldehyde and ketone. Right? Now, they react with formaldehyde to give a primary alcohol, and react with other aldehyde to give secondary alcohol, and upon hydrolysis give ketone with a tertiary alcohol. Now what we are saying is that if you have something like this CH3 MgI, this is something that we've learned before, plus formaldehyde is something like this. Now this Grignard reagent you see here, it splits, right? It splits most times into something like this CH3 negative. This group here is negatively charged. This negative charge comes here, and then at the end of the day, what you are going to form is this CH3 attaches to this place. So you have H, C, here gives us CH3, here is H, here gives us O negative, plus this magnesium iodide, because when these two things split like this, here becomes Mgi positive. This positive charge will be attracted towards this negative charge. Then upon acid hydrolysis, if you are conversant with chemistry, right, what will happen is that this will be converted to the corresponding alcohol. Now in this case, for formaldehyde, is going to give a primary alcohol. So this may be a very good objective question, that Grignard reagent react with formaldehyde to form dash alcohol, primary, secondary, tertiary. The correct answer is what? A primary alcohol. Now formaldehyde is the simplest aldehyde. It reacts with other aldehyde to form a secondary alcohol. Now other aldehyde means we can just come here. Other aldehyde means any other aldehyde apart from formaldehyde. So let me put CH3 here. This is other aldehyde, to make this easy, so that we are not going to write another this thing again. So what do we have here? CH3. What kind of alcohol is this? If you look at this alcohol very well, you agree with me that here is CH3, here is the CH3, alkyl group. When you have two alkyl group attached to the carbon carrying the OH, what kind of alcohol is that? A secondary alcohol. Now Grignard reagent also reacts with ketones. Now what will make this compound to be a ketone is by just coming here, changing here to CH3. They react with ketone to form tertiary alcohol. So it means here, what you are going to form is something like this. In this case now, you are having three alkyl group here, alkyl group here, alkyl group here, which gives it the ketone. So that is how basically Grignard reagent reacts with these aldehyde or these carbonyl compounds to form different alcohol. And Victor Grignard actually received a Nobel Prize for this experiment that he carried out. Now the last thing here is, the last synthetic utility of Grignard reagent is that they react with esters in the same fashion. Grignard reagent reacts with esters. Now, how do they react with ester? In the same fashion. So we have a Grignard reagent here. In this case, it will still be the same thing, plus the ester. The ester we are going to look at something like this. O, and then you have C2H5. Any one of the esters can actually go in here. What functional group is this? This is an ester functional group. Now, according to what we said this thing will break here, right? If it breaks here, you have CH3 negative, right? Because we said it will break here. And here becomes positive, here becomes negative. This negative here is capable of attacking here because it's a good nucleophile. and this bond here is partially positive and this here is partially negative because of the electron cloud that is put towards the oxygen the more. So this one here will pack up to form a negative charge, and then what you are going to have something like this. You have CH3, C, double bond O, negative. Then you have CH3. You are going to have O, C2, H5. And then this bond here will definitely come back. All right? This bond here can come back. Now, when this bond comes back, it's not going to undergo just the hydrolysis easily. Is that okay? It can come back, and then this is going to kick off this one from here. Or in most cases, you can still put your IgMO, but most times, you know, this MgI, which is the other branch that is positive. I know the positive and negative, we are always joined together. But this one will kick into this plate to form a double bond. Why this one have to kick out? So what you are going to form at the end of the day will be CH3, C double bond O, and then we'll have this CH3. What functional group is this? This is a ketone. This ketone now can further react with another Grignard reagent to form what kind of alcohol? A tertiary alcohol. True or false? True. Because if this one reacts with, let's say this one comes here. Oh, sorry. This one will pack up. We are trying to draw another. This one, I mean the product that is formed. This is the product. The product here is a ketone. This product that is formed can react with another Grignard reagent in the reaction vessel to form the tertiary alcohol. So they react with esters to form tertiary alcohol. First of all, they will form ketone. Then the ketone will further react to form tertiary alcohol. So here is CH3. Here is what? CH3. The last step is acid hydrolysis, which is H plus H2O, which will convert this group here to OH. So we have OH, C, CH3, CH3, and then finally CH3. So those are the synthetic utility of what? Grignard reagent. Kind of very easy, right? Exactly. That is the only thing that you should actually look at. I think we are done with this lecture. Thank you very much for your time. We'll see you in the next one.